Hello viewers, in the previous session we have proved the following theorem, this theorem that if f of z is analytic at z naught and f of z naught equals w naught, okay, and that f of z minus w naught has order n at z naught. Okay. Under these circumstances, if epsilon is positive, then there is a corresponding delta positive such that all the values in the delta neighborhood of w naught are taken exactly n times by f in the epsilon neighborhood of z. Okay. So, a picture for this is definitely in order. Okay. So, here is an epsilon neighborhood of z naught. So, this is the domain, okay, and this is the range. Okay. So, here is w naught equals f of z naught, okay, and f takes z naught to w naught. Okay. So, now if this epsilon is sufficiently small, okay, though then also the 0 of f of z minus w naught is of order n, then each point in this neighborhood. Okay. So, let us call A, let us pick an A in this delta neighborhood, this is a delta neighborhood of w naught. Okay. So, each point A is assumed n times here, there are n points here counting multiplicity such that f of z is equal to A for these points in the epsilon, for these points in the epsilon neighborhood. Okay. That is what this theorem asserts. Okay. So, a remark is in order here, we can further assume that the multiplicity of assuming A at each of these points is actually 1. What I mean by that is remark. Okay. So, I will remark that we can further assume that the multiplicity, okay, or I will say the multiplicity of the 0 of f of z minus A, okay, in this epsilon neighborhood. So, I am referring to the theorem under the conditions of the theorem, okay, in this epsilon neighborhood of z naught, okay, is 1 at every 0 of f of z minus A. Okay. What I mean by that is, if z 1 is a 0 of f of z minus A, i. e. f of z 1 is equal to A, okay, where z 1 belongs to be z naught epsilon. Okay. So, z 1 is a solution to f of z equals A, and z 1 belongs to the epsilon neighborhood around z naught. Okay. Then the multiplicity of 0 of f of z minus A, okay, at z 1 can be assumed to be 1, or it can be said to be a simple 0, okay, where there is an assumption where A is not equal to w naught. Okay. So, for anything other than w naught, so if I pick any A here, I am referring to this picture here now. If I pick any A here which is not w naught itself, okay, then each of these points which hits A, okay, is a 0 to f of z minus A, okay, and then the multiplicity of the 0 at that point z 1 of f of z minus A can be assumed to be 1. Okay. Why is it so? Well, firstly, this, okay, why? The answer is as follows. This is vacuously true if f is a constant function, right. If f is a constant function, there is no other a that we can pick other than w naught, because all the points are mapped to this w naught itself. It is a constant function. Okay. So, we can assume that f is a non-constant function. If f is non-constant, we can do the following. Notice that f prime, okay, f prime of f prime is not identically the 0 function. Why? Well, because if f is analytic, f prime is analytic, okay, and f prime identically 0 on an open set gives you that f is constant on the components on which f is analytic. Okay. So, f prime is not identically 0. If f prime is identically 0, f is constant on in the ball at least. Okay. So, since f is non-constant, okay, and since f prime is an analytic function, the zeros of f prime are isolated by the identity theorem, if you wish. Okay. So, since f prime is analytic as well, okay, in the epsilon ball, if you wish, f of z naught, sorry, b of z naught epsilon, the zeros of f prime are isolated. Okay. So, in particular, there is a let us say delta 1 positive, such that f prime of z is not equal to 0 in b z naught delta 1. Okay. So, even if f prime is 0 at z naught, there is a small neighborhood around z naught, such that f prime is not 0 in I should say this is the deleted neighborhood b prime z naught delta 1. Okay. So, i e this is i e for 0 strictly less than mod z minus z naught strictly less than delta 1. Okay. So, that is the deleted neighborhood of z naught. Okay. So, what this gives us is that then considering b prime or b prime z naught delta 1, which is an open set, okay, and using Taylor's theorem, if you wish. Okay, we can say that since f prime of z 1 is not equal to 0, well, here z 1 is the 0 of f of z minus a. Okay. So, we can say that since f prime of z 1 is not equal to 0, for a solution z 1, okay, to f of z is equal to a, where a belongs to the delta neighborhood of w naught, okay, and a not equal to w naught. Okay. The 0 of f of z minus a at z 1, okay, is simple. you expand f of z minus a. F of z minus a is also an analytic function. So, you expand f of z minus a around z 1. Okay. So, since f prime of z 1 is non-zero, you have that the 0 at z 1 of f of z minus a has to be simple. Okay. That is by the Taylor's expansion for f of z minus a around z 1. Okay. So, that says that so these zeros can be assumed to be simple. Okay. The zeros of f of z minus a can be assumed to be simple. Okay. So, what that is telling us is that here once again the picture. Okay. Here is w naught, here is z naught. If I pick any z which gets mapped onto some a in a delta neighborhood of w naught, this is the delta neighborhood of w naught, this is the epsilon neighborhood of z naught as in the theorem. Okay. And if f of z is equal to a, okay, then there is a small neighborhood of this z such that z is the only well, I do not need a neighborhood here, this is a. Okay. So, in this small neighborhood here, of z, z is the only solution to f of z is equal to a. Okay. So, if this is z 1, so then f of z 1 is equal to a and f of z is not equal to a in the hashed neighborhood, hashed as in this picture, this pictured neighborhood. Okay. Now, we are ready to prove the open mapping theorem as a corollary to the theorem we had last time. So, a non-constant analytic function maps open sets to open sets. Okay. I.e., okay, so stated in another way, let f be an analytic function. Okay. Non-constant, let f be a non-constant analytic function. Okay, on an open set G, then f of G is open in C. G is open set in C, then f of G is open set in C as well. Okay, so this is another way of stating the same. All right. So, what is the proof? Well, the proof follows from the theorem above. Okay. So, what do we need to show? Let f be a non-constant analytic function on an open set G. We have to show that f of G is open, f of capital G is open. Okay. So, let A belong to G, okay, and then f of A belongs to f of G. So, we want to show that there is a delta positive such that B of f of A delta is contained in f of G, and every W belongs to B of f of A delta, okay, has a pre-image in G via f. Okay, so, this is what we want to show. So, this comes directly from the previous theorem. So, by the above theorem, okay, by choosing sufficiently small epsilon, Okay. There is a delta positive such that every value of b of f of a, well, f of a itself is assumed by a by f at the point a. Okay. So, b of f of a delta, okay, is assumed the same number of times inside a circle of radius epsilon. Okay. Around A. Okay. So, f of A itself, like I remarked, is assumed by f at A. Okay. So, all the values in this ball are assumed by f at least once. Okay. So, that is the point. B of f of A delta, okay, is contained in the image of the ball of epsilon radius around A, okay, via f. Okay. So, this is the point, and then this is contained in f of g. So, f is an open map. Okay. So, that completes the proof of this theorem, and that is a very important result. We will see that the maximum modulus principle follows as a consequence. There is a remark following this corollary. Okay. If the 0 of f of z minus w naught, okay, is simple at z naught, okay, in the above theorem, okay, i.e. n is equal to 1. Okay. So, in this theorem here, in the first theorem that I quoted, okay, so if n is equal to 1, if the 0 of f of z minus w naught is simple, okay, then there is a 1-to-1 correspondence okay, between an open set of f of z minus between open set of b z naught epsilon. Okay. So, between an open subset of this ball, okay, and the disk b f of z naught, namely w naught delta, right, because each value in b w naught delta is assumed exactly one time by some point in b z naught epsilon. Okay. So, there is some open subset here. By the open mapping theorem, we can say that an open set is carried to this here, okay, and then so an open set open subset of b z naught epsilon is mapped in a 1-to-1 fashion to b z naught delta. Okay. That is a remark, okay. And then we will see some more results following from this important theorem we saw in the last session. Okay. So, here is a case where we are assuming n is equal to 1. Okay. So, here is a proposition, let G be an open set, okay, and let F be analytic and 1-to-1. Okay, in G. Then F is conformal in G. here is the proof in detail. Okay. So, f is 1 to 1 implies f is locally 1 to 1. What I mean by locally is that there is a neighborhood around every point where it is 1 to 1. If f prime of A is some arbitrary point in G, okay. If f prime of A is 0 for some A belongs to G, okay, then given a small epsilon positive, okay, there exists a delta positive such that f takes every value in B f of A epsilon or sorry delta, okay, at least twice in B A epsilon. That is because if f prime of A is 0, then the order of 0 of f of z minus f of A at A is at least 2. So, by the remark earlier, we can assume that in a small enough neighborhood of A, we can assume that the number of zeros of f of z minus some w, okay, is simple, okay, or is equal to 1, okay, or the multiplicity of such zeros is equal to 1. Okay. So, what that means is that every value in B f of A delta has to be taken at least twice in B A epsilon, okay, in B A epsilon. Okay. So, that is a contradiction since f is locally 1 to 1. Okay. So, that says, so f prime of A is not equal to 0 for any A belongs to G. So, next we have another consequence that we can speak. Okay. Here is another proposition. So, let once again here we are dealing with 1 to 1 analytic functions. Let G be an open set, okay, and let f be analytic and 1 to 1. In G, then f inverse is analytic in f of G. Okay. So, firstly note that since f is 1 to 1, okay, on G, f inverse from f of G to G, okay, is well defined. Since f is 1 to 1. Further, as a consequence of the open mapping theorem, we can note that f inverse is firstly continuous. Okay. So, f inverse is continuous. Here is the argument. Okay. So, so what I will show is the inverse image of an open set in G. Okay. So, here is f inverse from f of G to G. If I pick an open set here, I will show that the inverse image of that is open in f of G. Okay. So, let V be an open set in G. Okay. Then f of V is open in f of G because of the open mapping theorem, okay, by the open mapping theorem. Okay. So, also notice that f of V is f inverse of it is F inverse of V. What I mean by that is it is the inverse image under F inverse of the set V. Okay, since this is because F is 1 to 1, okay, is 1 to 1 correspondence more so. It is a bijection, okay, 1 to 1 correspondence from V to F of V. So, the inverse image of F inverse of V is nothing but F of V. Okay. So, so F inverse inverse. So, F inverse inverse of V, okay, is open in F of G, okay, and hence that tells that F inverse is continuous. We have shown that the inverse image of an arbitrary open set in G is open in F inverse in F of G, and okay, under F inverse. So, F inverse is continuous. Let A belong to G and F of A, okay, and let F of A is equal to B. Then F inverse of B is equal to A. Okay. So, I want to show that F inverse is analytic at F of A, and every point in F of G looks like F of A. So, I will be done if I show that F inverse is analytic at the point F of A. By previous proposition, we have shown that since F is 1 to 1, we have shown that once we have a 1 to 1 function on an open set, F prime is non-zero or F is conformal. So, F prime of F inverse of B, namely F prime at A, is non-zero. Okay. Now, here is where I will actually use continuity, which I showed separately here, okay, of F inverse. Okay. So, now since the limit as z goes to B of F inverse of z is equal to F inverse of B. Okay. So, this is why I need continuity in the first place, and then I can show differentiability in the standard order, okay, by continuity of F inverse. Okay. So, the limit as z goes to B of F inverse of z minus F inverse of B by z minus B, this is the difference quotient and the limit of the difference quotient. Okay. So, I want to show that this limit exists, and then I will be able to conclude that F inverse is differentiable. Okay. So, this is equal to the limit as z goes to B of F inverse of z minus F inverse of B. I am preserving the numerator and I am writing the denominator as F inverse of F of F inverse of z minus F of F inverse of B. Okay. So, this is equal to, so what I will do is I will say this is limit as F inverse of z goes to F inverse of B. Limit as z goes to B is the same as limit as F inverse of z goes to F inverse of B, okay, because F is 1 to 1 and F inverse is continuous. Okay. So, this is 1 divided by F of F inverse of z minus F of F inverse of B divided by F inverse of z minus F inverse of B. Okay. So, notice that the denominator is nothing but the differentiation of F at F inverse of B, okay, and we know that is non-zero. So, this is equal to 1 by F prime of F inverse of B. Okay. So, this makes sense, this thing makes sense because F is conformal at F inverse of B. Okay. So, F inverse is, as a conclusion we can say that F inverse is analytic at B, i.e. f of A. And since f is on to f of g, okay, f of capital G, every point in f of capital G looks like f of A for some A in G. Okay. So, f inverse is essentially analytic on all of f of G. Okay. So, that completes the proof of this proposition. So, in the case that f is 1 to 1, we can say more, we can on an open set G, we can say more, we can say that f is conformal on that open set. We can also say that the inverse function is analytic. Okay. So, these are two conclusions we can make from the theorem that I wrote at the beginning of the session, okay, in the case where n is equal to 1. All right. So, next we will see that we can deduce the maximum principle, okay, as a consequence of the open mapping theorem. Okay. So, theorem, the maximum principle. So, if f of z is analytic, and non-constant, in a region G, okay, then its absolute value modulus of f of z, okay, has no maximum in G. Okay. So, we want G to be a region, then modulus of f of z has no maximum in G. Okay. So, we stated the maximum principle before, okay, in a slightly different version, and there I remarked that it can be directly proved using the local version of the maximum modulus principle that we have already seen. Okay. So, but we wanted to take a different route. We wanted to prove the open mapping theorem first and deduce this theorem as a corollary to that. Okay. So, there is a merit to it. This shows that I mean this process of showing the maximum modulus principle tells you more about the local property of the analytic functions, okay, that that open sets are actually mapped to open sets. Okay. So, you cannot have that the interior point is mapped onto some boundary point, okay, as a consequence of open mapping theorem. Okay. So, hence the maximum modulus principle. Okay. So, let us prove this theorem using the open mapping theorem. So, here is the proof, belong to G, okay. Then B z naught r is contained in G for some r positive. Okay. If W naught is equal to f of z naught, okay, then there is a delta positive, okay, such that B of f of z naught is delta is contained in f of B of z naught r by the earlier theorem, okay, which we had. Okay. So, so modulus of f of z naught clearly, okay, cannot be maximum value of modulus of f of z. Okay, that is because in this ball there are always points which have modulus greater than the modulus of f of z naught. Okay. So, in any ball the points further up here, Okay, if origin is here, if 0 of the complex plane is here, then there are always points up here which have greater modulus than f of z naught itself. Okay. So, that is the idea. So, it proves this theorem. Okay. So, so maximum modulus principle follows easily by using the previous theorem. Okay. Notice that I am calling all these as consequences of open mapping theorem, but I am resorting to this theorem. Well, actually the hard work of the open mapping theorem is captured in this theorem. Okay. So, this is more general, but this theorem is the fundamental idea behind the open mapping theorem. Okay. So, coming back to here, now we can prove the Schwarz lemma, which is actually an important consequence to the maximum modulus theorem. Okay. So, we can say something more about the function f, okay, and its bounds, okay, when we have more conditions as follows. Okay. So, the Schwarz lemma is an application. So, here is Schwarz lemma. So, suppose that f is analytic on B 0 r, a disk of radius r centered at 0, okay, and that f of 0 is equal to 0, okay, and that, okay, and modulus of f of z is at most capital M for z belongs to B 0 r bar. Okay. Then modulus of f of z is less than or equal to m by r modulus of z for mod z less than or equal to r. Okay. So, if the modulus of f of z has a maximum of capital M on the closed disk B 0 r bar, the closure of B 0 r, then the modulus of f of z is at most m by r mod z. Okay. So, before proving this, let me quickly remark also that this maximum principle tells you that if G is a bounded region, okay, if G is a bounded region, it tells you that mod f of z has no maximum inside in the interior of G closure. So, modulus of f of z has to have a maximum on the boundary of G, if G is bounded. Okay. Why? Well, modulus of f of z firstly is a continuous function from G closure into the complex plane. So, a continuous function on a compact set, okay, G I am assuming is a bounded set. Okay. So, on a compact set G closure, f modulus of f has to have a maximum, okay, and the maximum cannot occur in the interior of G bar, namely G. Okay. So, the modulus of f has to have a maximum on the boundary whenever G is bounded. Okay. So, Schwarz lemma is something in that line. It is telling that if I assume that the modulus of f of z is bounded by M on this closed disk B 0 r bar, okay, and f of 0 is 0, we can relax that in some sense, but at least for this version f of 0 is 0, f is analytic on B 0 r, then modulus of f of z is less than or equal to m by r modulus of z for mod z less than or equal to r. Okay. So, further actually there is more to this lemma. We can say that if equality occurs, okay, for some z with mod z less than r. Okay. So, in this inequality, if equality occurs, okay, then there is a real constant m such that f of z is actually equal to m z e power I m by r. Okay. So, it is actually the function m z by r up to some rotation e power I m. Okay. Since f of 0 is equal to 0, okay, we have this as well. Okay. So, proof. So, since f of z is 0 or f of 0 is 0, okay, there is an analytic function g, okay, on B 0 r such that f of z is equal to z g of z, okay, for all z belongs to B 0 r. Okay. So, by considering the Taylor series expansion around 0, if you wish, you can say that there is a function g like that. Okay. The order of 0 at 0 is at least 1. Okay. So, we have this. So, on mod z equals r 1 strictly less than r, okay, modulus of g of z, okay, is less than or equal. So, on a circle of radius r 1 strictly less than r, by using maximum modulus theorem for the function g, okay, what we can say is that the modulus of g of z is less than or equal to modulus of f of z by r 1, okay, which is less than or equal to m by r 1. Okay. So, for z belongs to B 0 r 1. Okay. For all the z belongs to B 0 r 1, by maximum modulus theorem we have this. Okay. And now, letting r 1 tend to r, we can conclude that modulus of g of z is less than or equal to m by r for z belongs to B 0 r. Okay. So, from this we can say that modulus of f of z is less than or equal to m by r modulus of z. By substituting what g of z is, we get this, okay, for modulus of z less than or equal to r, z not equal to 0. Okay, since we are multiplying by modulus of z, and for z equals 0, this inequality is true, is trivially true, because f of 0 is 0. Okay. So, all in all, modulus of f of z is less than or equal to m by r mod z for z belongs to B 0 r bar. Okay. Now, if equality occurs, if modulus of f of z happens to be equal to m mod z naught by r, f of z naught is equal to m mod z naught by r for some z naught, in B 0 r, okay, then mod g attains maximum at some point, okay, implies inside the disk. Okay. So, implies that g is a constant function. That is the only way at an interior point you can have a maximum modulus. Okay. So, g is a constant function. Okay. So, so g of z naught, okay, is, or sorry, g of z. So, f of z looks like c times z, okay, for z belongs to B 0 r. Okay. Also, modulus of C, modulus of f of z naught is equal to m times modulus of z naught by r, because equality occurred, which implies modulus of C times modulus of z naught is equal to m times mod z naught by r, which implies modulus of C is m by r. Okay. So, C looks like m by r e power I m for some m, okay, for some m real. Okay. So, so f of z then is equal to m by r z e power I m as claimed. Okay. So, that completes the proof of this lemma. Okay. So, we can say something more about f of z when we know its bound on the boundary of P 0 r, and if f of 0 is 0. Okay. So, that is an application of the maximum modulus theorem.